Hello, and welcome to Agrosive Physics. Today is day 108, and what I'd like to discuss today is electric potential. Now, we've already discussed the electric field, which is the region around an electric charge that can affect other charged particles and apply a force on them. Well, the electric potential is the amount of work that a field can do. And what's a lot nicer about the electric potential is that it's a scalar quantity. So we don't have to spend as much time worrying about vector addition. Now, since it's related to work, we could think of it in the following way. If I have a Van de Graaff generator that is my source, and that's just the typical example that we'll use, and it's a positive source, if I take a proton and place it in the electric field that surrounds it, there'll be a certain force that acts on that particle. If I now take that charged particle and I place it closer to the source, that's going to increase its potential, its electric potential. And I like to think of electric potential, it's similar to potential energy due to gravity, but it's the electric field version of potential energy. Now, when I push that closer to the field because it's a positive field, that's going to increase the amount of work that the field's going to do on it when I let go. If I bring it farther away, I'm going to decrease the potential of that positive test charge. Now, consequently, if I have an electron and I place it in the electric field around a Van de Graaff generator that's positive, if I were to bring it farther away, I have to do work to pull it away, and then the field will do work when I let it go and cause that particle to move. So electric potential is just the combination of all the scalar quantities of the ability for a single field or multiple fields to do work on an object. Now, the electric potential by itself really doesn't help us because a single point in space doesn't really tell us how much work it can do. What really matters is the potential difference. And we have another word for the potential difference that you've probably heard before, and it's voltage. So potential difference and voltage are synonymous. Now, if I were to take the potential at a single point, move the charge to a new point, and find the difference between them, that would be the potential difference between 2 points. We're going to be able to calculate that in a few moments. Now, what's different about this compared to potential energy due to gravity is that if you remember, the potential energy due to gravity was based on the mass of the object. Bigger objects had more potential energy because we used mgh. In this case, the field is what really determines the amount of electric potential that an object can have, and subsequently the amount of potential difference that it exists. So the potential difference is really based upon the field, not upon the individual charges that we place in it. So if we have a large charge, that's going to require a large amount of work, but mathematically it's not going to matter. If we have a small charge, that's going to do a little bit amount of work, but it's not going to matter because of the equation that we're going to have momentarily. So the potential difference is based on the field, not the charges themselves. Now, that being said, if we look around the Van de Graaff generator, concentric circles around the Van de Graaff generator would show lines of equipotential. Any place around a certain distance, as long as we're in a concentric circle around it, would have the same electric potential. If I bring it to a new spot farther away or closer, that would change the potential of the object and thereby giving it a potential difference. So moving around, if we think of it as a circumference around the Van de Graaff, you would have no potential difference. You have to go perpendicular to the sphere itself in order to have a potential difference. Now, mathematically, because it's the voltage, we use V as our variable. Potential difference, voltage, is denoted with a V. And the equation is W over Q. So it's the work done divided by the charge of the object that's in the field. So potential difference is V equals W over Q. And our units are joules per coulomb, which we call volts. So when you talk about electricity and you talk about volts, you're really talking about the potential difference in the field. Now, when we're dealing with charged particles, often we'll deal with electron volts, and that is a measure of the amount of work required to move an electron a potential difference of 1 volt. And it's not a potential difference, it's actually a unit of energy. So we have 1 electron, 1 volt, and if we look at the electron's charge is 1.6 times 10 to the negative 19 coulombs, and it moves 1 volt, then the amount of work that would be required is 1.6 times 10 to the negative 19 joules. So the conversion between 1 electron volt to joules is 1.6 times 10 to the negative 19 joules. So that could be a conversion factor that will be important as we move forward in the course. It is not a measure of voltage, it is a measure of energy. And we just use it because we're going to often deal with electrons moving in fields, and that will be a nice common measurement as opposed to using joules, which has a very small value. So the electron volt is just going to make it easier for us to deal with mathematics and also to compare numbers. Very similar to how we use the index of refraction to talk about the relative speed of light in a material. So we have the electron volt, which will allow us to deal with many different electrons with easier numbers. Now at this point, let's look at a couple of sample problems. I'll bring out the whiteboard and we'll do a few example problems dealing with potential difference. We'll be able to find the voltage at different points in an electric field. Thank you. So we have a new term called electric potential, which is how much work is required to move a charge from one point to another in a field. So it's the work per unit charge. So V is the potential, which is also known as the voltage. That's measured in volts. We have W, which is the work, which is measured in joules. And we have Q, which is the charge, which is measured in coulombs. So the volts is also a joule per coulomb. Now that's not to be confused with an electron volt, which is a unit of energy. And 1 electron volt is 1.6 times 10 to the negative 19 joules. And it's defined as the amount of work required to move 1 electron a distance of 1 volt in a field. So if this is 1 electron, it's 1.6 times 10 to the negative 19 coulombs. And if it's 1 volt, cross multiply, you end up getting the work to be 1.6 times 10 to the negative 19 joules. So one common mistake that students make is they confuse electron volts and volts. Electron volts is work or energy needed, and V is the potential difference, the amount of work per unit charge required. So electron volt is an energy term, and the voltage is the amount of work per unit charge. All right, a typical practice problem dealing with potential difference involves speed of subatomic particles. So if we're moving a proton through 6 volts of potential, how fast does it move? And we need to start with our V equals W over Q equation. The V is 6 volts. The W is our unknown, and the Q for a proton is 1.6 times 10 to the negative 19 coulombs. Cross multiply, we can find the work. So 1.6 e negative 19 times 6. And you get the work to be 9.6 times 10 to the negative 19 joules. Now, when the proton experiences that amount of work, it turns into kinetic energy, which is 1/2 mv squared. So 9.6 times 10 to the negative 19 joules equals 1/2. Mass of a proton is 1.67 times 10 to the negative 27 kilograms, v squared. So let's see what we get. Divide that by 0.5. Divide that by 1.67 to the negative 27. And take the square root. And I end up getting a speed of 3.4 times 10 to the 1/234 meters per second. So pretty fast. So if we place a proton in a 6 volts of potential difference, it will move at 3.4 times 10 to the 4 meters per second. All right, this next one we're going to look at electron volts, and we're going to move 10 electrons, a potential difference of 1.5 volts. So if we look at our V equals W over Q equation, we want to know that V is 1.5. We know that Q is 10 electrons, so we're trying to find the work. And if it's 10 electrons, it's 10 times 1.6 times 10 to the negative 19 coulombs. Now all we'd have to do is move that to negative 18, but I'll just leave it like this. And if I do 1.5 cross multiply here times 10 and then times 1.6 e negative 19, I'm going to get 2.4 times 10 to the negative 18 joules. Now the problem asks, though, for what is the value in electron volts. So this becomes a conversion. 1 electron volt is 1.6 times 10 to the negative 19 joules. And if we divide this by 1.6 e negative 19, we get 15 electron volts. So you'll see that if we have 10 electrons and we each need to move at 1.5 volts, we would multiply the two and get 15 electron volts. This shows how this variable makes our life a lot easier. 15 is a lot easier to deal with than 2.4 times 10 to the negative 18 joules. What I'll do, since I'm running out of room, is I'll reset and we'll find the second part of this sample set, and that's the kinetic energy. Hold on one sec. All right, so for this we're going to place a proton in a potential difference of 10 volts, and we want to see how fast it's going to move. Now, the proton is going to be affected by that potential, and it's going to move. So the potential is 10 volts. The work is what we're looking for, and the Q is, for a proton, 1.6 to the negative 19 coulombs. So if we multiply, we should get the work to be 1.6 times 10 to the negative 18 joules. Now that work will turn into, because of the work energy theorem, kinetic energy, which is 1/2 mv squared. So we know it's 1.6 times 10 to the negative 18 joules equals 1/2. The mass is 1.67 times 10 to the negative 27 kilograms. And we multiply by v squared. So let's do the math now. 1.6 e negative 18 divided by 0.5 divided by 1.67 e negative 27. And we're going to take the square root. And the square root gets us 4.4 times 10 to the 4 meters per second. So it moves quite quickly, but a proton's very light, which is why.